Welcome to ASU's University Academic Success Programs. This video will cover the topic Rotational Motion. In physics, we begin learning all about objects in linear motion. We learn about forces that act in vertical, horizontal, and even diagonal directions, displacements, velocities, and accelerations. Now, let's think about these things in rotational motion. Rotational forces, which are called torques, angular velocities, angular accelerations, and centripetal accelerations. Although rotational motion is not linear motion, these two forms of motion are related. Let's go over these relationships. We'll start with period, t. In your own words, can you describe what a period is?
A period in this context is the amount of time it takes for an object in rotational motion to go around its cycle once.
Yes, exactly. Period is the amount of time to go through one cycle, or around the circle once. So now we will write out angular velocity, or angular frequency. Angular velocity, omega, is defined as the total radians of the circle, 2 pi, divided by the period, in units of radians per second. Now that we know angular velocity, we will write out the relationship between linear velocity and angular velocity. Linear velocity v equals r times omega, where r is the radius of the circle. For an object in rotation, the linear velocity vector is tangent to the circle, and the linear acceleration vector is pointed towards the center of the circle. It is actually called centripetal acceleration, and there is always a centripetal acceleration present when an object is in rotational motion. Centripetal acceleration has the formula AC equals v squared over r. When doing a force analysis and the net force equation for Newton's second law, we substitute v squared over r in for A, so F net equals m times v squared over r. Let's now do an example problem where we will use centripetal acceleration. The above picture is a 1,000 kilogram car passing the top of a hill with radius of curvature 250 meters at a speed of 50 meters per second. Find the magnitude of normal force on the car in newtons. The gravitational acceleration is g equals 10 meters per second squared.
This is just a car driving over a hill. Is it really in rotational motion?
Yes, it is. It doesn't really seem like it at first, because we are tempted to think that an object must be traveling around a whole circle for it to be rotational motion. However, as long as something is traveling on a curved path with a radius of curvature, such as in this problem, there is some rotational motion involved.
Okay, that makes sense. How should we start this problem?
Let's first be sure that we have all the given information written down. We have mass, m, equals 1,000 kilograms. We have radius, r, equals 250 meters. We have velocity, v, equals 50 meters per second. And we already have acceleration due to gravity, g, equals 10 meters per second squared. Normally, it is about 9.81 meters per second squared, but to simplify things, we can round it to 10 meters per second squared in this case. Now, we must draw a free body diagram to show all the forces acting on the car. We have the normal force, Fn, pointing directly upwards from the car. We also have the weight force, which is equal to mg, pointing downward. We also can't forget about the fact that there's a centripetal acceleration pointing downwards as well. Now we are asked in this problem to find the normal force. To do that, we will write out our centripetal force net equation. There are only forces in the vertical or y direction, so we have the equation sum of forces equals m times v squared over r. We will now substitute in our sum of forces. Fn minus mg equals m times v squared over r. We add mg to both sides to find Fn equals m times v squared over r plus mg. We can factor the m out on the right side to simplify this to Fn equals m times the quantity of v squared over r plus g. We will now substitute in the numbers. Fn equals 1,000 times the quantity of 50 squared divided by 250 plus 10. And after performing this calculation, we find Fn equals 20,000 newtons. This is our final answer. So the force pushing back up on the car is much greater than the car's own weight.
Okay, that makes sense to me, but why couldn't we have simply substituted in the numbers at the beginning of the problem? Why did we leave all the symbols in until the very last step?
Good question. We did this because in some problems, if you substitute in numbers early on, this could lead to some false rounding and errors in your calculation steps. If you stick with symbols and then do only one calculation at the end, this eliminates this problem. Using symbols also helps us to better understand the physics concepts, forcing us to understand the meanings of the equations instead of just throwing numbers in.
Okay, that makes sense. I'll be sure to keep that in mind while working on more physics problems. So in summary for this topic, when an object is in rotational motion, it has a centripetal acceleration. Knowing that centripetal acceleration is equal to v squared over r, we can use it in a net force equation to analyze forces acting on the object in circular motion.
Great summary. It sounds like you are ready to do some more practice problems on centripetal acceleration and to learn more about rotational motion.